Good morning. Welcome back today, you guys. I want to just tell you why there's a camera here today. It has nothing to do with you. It's just for me. I actually wanted to have a video of this type of class session to use for some faculty development and then for my own personal review as I strive to grow as an instructor. So it's not here for you at all, and it's going to be focused mainly on me and moving around the classroom today. So just pretend that Jay is not here. Professor Rasmussen is in the education department. I work with him in faculty development, so I recruited him to come in today to do the video. So let's talk about announcements. You guys have a big week coming up on Wednesday. Is your poster symposium. Today and tomorrow in lab, we will finish up the posters. We'll get a chance to do some peer review, and you guys will see your posters printed before you leave lab, so that will be exciting. The biology department picnic is going to be hosted in conjunction with symposium. So you guys are going to have a chance to go to the bio picnic if you want, optimally forage on some free food, and then come down to the underground for your poster session. The picnic, I believe, is starting at 4:30, and your poster session starts at 6. So you should have time in that window if you so choose. We're going to encourage people to come from the picnic to the symposium because we're having dessert at the symposium. So we hope to see a lot of faculty and students actually come and support you guys in your poster session as well. We'll talk about details in the symposium. We're going to practice getting you guys prepared to stand by your posters. All of that's going to happen in lab today and tomorrow. Bobby?
What time is the symposium?
Starts at 6, and we should be done before 8. I'm thinking 7:45, 7:50. We will talk about that in lab once we see how many adults we have. Good question. Okay, the other couple of announcements have to do with homeworks. So homework 12 is due today. If you guys would make a pile of those on top of your tables. And then homework 13, a number of you already completed that, but both of those links are available on Moodle for you. And then please make a note to bring your computers on Wednesday. We're going to be doing a survey through a carbon footprint online in class on Wednesday. So please bring your computers for that. Do you guys have any other questions this morning? Okay, then let's start our week in prayer, our final week, and push to the end. Lord, thank you so much for bringing us together for one last week. Thank you for the learning that has taken place over the course of this semester. And I do pray for these students. I know this week is extremely busy. There's a lot going on. And I'm praying that you're going to help them to manage their time well, to be intentional with their choices, and to be able to bring you glory in all that they do. I pray for their minds, Lord. Help them to not become stressed. Just keep them focused on you and the things that they have before them. And just pray for encouragement and just genuine enjoyment of this last week of the semester. We commit our time to you, Lord. Help us to learn and grow in knowledge and likeness of you. In Jesus' name we pray. Amen. Okay, so we have a handful of learning objectives today. If you guys remember, we are in the section of the course that's focused around what question? What's our driving question for this last unit? What's the main focus? Carbon. So why is carbon so important? And so today we're going to build on where we've been. We're going to talk about carbon dioxide fertilization or CO2 fertilization, nitrogen fertilization. We're going to look at air pollution and specifically nitrogen today. You guys are going to get to look at a little bit of data related to nitric oxide pollution, and you're going to draw some conclusions from that today. I'd like you to start with a 4-minute summary from Friday to re-engage. These are questions that we discussed, and question 4 is kind of the lead-in question for where we're going today. So go ahead and do this 4-minute summary. Carbon. Because, we're putting more into it.
Yep. It is.
Do you want to explain to them?
Greenhouse greenhouse gas and our water vapor from the methane.
Every single day.
Pray someone panic. Suddenly perhaps some notice. Pink. Days.
Oh. Yes. Makes sense. No. Oh no.
Okay, let's come back together as we revisit these questions. If you guys remember on Friday, we ended class with question number 4. Will photosynthesis increase as a result of increased CO2? And we had a clicker question where you guys voted in with the 3 choices, and this was our distribution on Friday. You guys read a homework assignment for today that kind of went at this question with a little bit more detail, the Beadlow paper. And I'm going to ask us to re-vote using these same 3 options this morning after having read the paper. So A is excess CO2 will increase photosynthesis. B, excess CO2 will not increase photosynthesis. And C, it depends. Okay, so here's where we are today after having read the Beadlow paper. Looks like A had a very slight change, B maybe decreased a little bit, and C increased quite a bit. We're going to dive into this question. You guys are going to unpack it a little bit together, and by the end of class today, you'll be able to have maybe a little bit more certainty with the response choice here. Okay, so we're going to look at the Beadlow paper, and there's a claim that can be made about CO2 and whether or not it will increase the photosynthesis of our plants and thus increase NPP. I'd like you guys to identify the claim and provide some evidence. 2 to 3 pieces would be great, and jot that out in your wall space. Go ahead and do that at this point.
I feel like everything is
Sorry.
Marker whacking. There's a red marker. Quoting from the article, higher concentrations of CO2 do not necessarily correlate with increasing seems like a big product because it's something. Or like necessarily always, but yeah, necessarily. Yes.
It's like 1900 availability.
They talked about
I think that would be related today. That would be something we would right here. Yeah. Those are the two big things.
Yeah, air pollution, evacuating water.
Add those onto your list.
Kind of mentally, we're experiencing a lack of wall availability for our resources.
Where are you guys at?
I'll just read you off these guys. Alright, you ready? Tier 2 enrichment in the North Town. Portland. Sure. Trees and Lilies. Near Springs, 30 minutes. Tier 2 presentations. No traffic. It's alright.
Found this in there. It says, although driving CO2 will reduce our production, inspired by soil.
To what?
Okay, take about another 30 seconds on your evidence and claims.
Wait, what's our second one? Water, air pollution, and what? What about them? Their factors.
Their factors. Yes,
just
full time.
just
Do I write that?
no.
I can't believe wait like this.
Alright, so let's take a look at the claims. There are 5 or so, maybe 6 claims written up around the room. Take a look at them. Is there a common theme as we look at the claims. What is the common theme, Bradley?
Huh?
I said, what is the common theme?
Well, there are other factors that affect photosynthesis besides just increased CO2 levels. Who's Elijah?
Eli. He signed his name.
Oh.
Wow. Okay, so Bradley, you were spot on. There are other factors, it appears, that play a role other than just increased CO2 in relatedness to will photosynthesis increase. So all the claims you guys made are virtually the same. So increased CO2 is not going to increase primary productivity, is not going to increase photosynthesis. So let's go back one slide here. Okay, if all of your claims say that increased CO2 is not going to increase photosynthesis, how come so many of you chose option C? Because based on your claims, I would have expected all of you to choose option A, right? That's the one that matches your claims. So what else is going on here? Why is it an it depends situation? Alyssa?
Because won't it increase photosynthesis in the beginning, but then ultimately decrease when everything is depleted?
Yeah, Alyssa, say that again a little louder.
Photosynthesis will increase in the beginning, but then as things get depleted, it will decrease.
So we might see a varying rate. We might see an increase in photosynthesis first and then a decrease to later follow. So let's actually, using your information that you know, using the claims that you have created and your evidence, I would like you to create a graph on your wall space of your claim. So look at your x-axis and your y-axis. Identify those first, and then sketch out your claim in relationship also to what you read in the Beadlow paper that Alyssa just shared with us about photosynthetic levels. So go ahead and sketch that out on your wall space.
Would it spike? Would it spike? It wouldn't just level out, it would come back down.
And it, like, okay, so it would be like
Maybe.
spike
I was thinking more about it.
and then level back down.
I don't know that.
Or would it start with a spike?
I don't even know. Yeah.
Would it start with
Yeah. I think. Well, no. That was supposed to do.
Fairly
It'll go curveball and then
as the CO2 increases,
end up lower.
initially,
So, and we're done. We're done.
All of you combined time. Cool.
And then why is that
Sufficient.
because global warming is bad, Kirby. Circular reason for the win. Okay. This is CO2, right?
Okay, maybe.
No idea. Right? Maybe it is.
What do you measure?
Help me out. Yes, I said yes. I said yes. Yes.
That's what we're measuring.
Yeah, carbon dioxide.
Yeah, what do we call that broadly?
Right?
Yeah.
I mean, I guess time.
Sure.
Yeah, I'm not. Why?
Would this be time?
Okay, I don't think it was enough.
Why? Yeah, why? I thought. Wait,
Yep, that's good.
But would it end up lower than the initial, or I don't think.
Most of you guys have time on your y or on your x-axis, and time is spot on. But what is it? Is it just time in general, or is it time under a certain set of conditions? Go ahead and modify your x-axis to reflect really what's going on.
Under increased levels of CO2.
so time would increase.
Do you want to erase it? Under CO2.
So CO2.
You don't need to erase that. That is good. That's good? Yes. Alright. So this is time under exposure to increased CO2.
So right,
Just write high concentration CO2. Just tell me on it.
that's time over CO2. You're writing time over CO2?
That was another weird part.
Time's supposed to be on there.
Time will decrease CO2.
What if you're writing
Oh, to put CO2 in. Okay, let's take a look at these graphs as you move around the room. Common theme. What happens initially to photosynthesis? It spikes. Okay, so what we could expect if we were looking at a graph is a spiking of photosynthesis. Some photosynthetic level will kind of plateau. It won't keep increasing. It will have increased for a little while, and then it will plateau for a period of time. So we may not see a sharp decrease. We may just see a plateau. Both of those are options for what might happen. And this is an area for research right now. People are spending a lot of time and money to try and figure out what's going to happen under these increased CO2 conditions. In fact, one of the studies that is working on this is about 30 to 35 minutes north of Bethel, the Cedar Creek Natural Research Area. They have an experiment where they're pumping increased levels of CO2 into a field to measure the NPP response rate. So this research is happening pretty close to home. Let's think now about some of your pieces of evidence. Okay, we've got the shape of the distribution, and now we're going to go to the evidence. And in particular, we are going to focus on our warrant in this scientific argument. So we've got our claim, we've got our evidence, now we've got our warrant. And our warrant here has to deal with the evidence that you guys listed. So I'm seeing things like nitrogen availability is limiting. Okay, air pollution is limiting. Water is limiting. You guys should be familiar with the law of the minimum, right? From chemistry? You guys talked about this yet? No. Rate limiting reactions. What limits a reaction? What limits a reaction? The limiting reagent, right? And the limiting reagent is typically the reagent that you run out of first, right? It's the one with the smallest quantity. In ecology, we call this Liebig, and that's the individual who coined this term, but it's the law of the minimum. And it's very similar to what you are learning in chemistry about rates limiting reactions. The limited reagent is very parallel to the law of the minimum. Reactions are limited by the element in the smallest quantity. So photosynthesis could increase initially because we've got more CO2, but it's only going to increase until something else limits it. And you guys have identified a number of other limiting factors. Nitrogen, air pollution, and water being the three big ones that you have listed. I have a question for you about limits to photosynthesis, so take a moment and check in here. Majority of you in here, just about 80% of you are saying all of the above. So all of these have potential to limit photosynthesis. Take a moment and think about, you already know probably 3 of these 4. You could probably identify where in the photosynthetic process they act. So think about these in relationship to photosynthesis, and at your tables determine where they act. Where would they limit? What part of the reaction would they limit? This is good review for the final. Talk about that. Where would they limit?
CO2 in the light reaction. Yeah. Just water goes into the what goes into light? Oh, light goes into light. That's why the enzymes are needed.
Since all of them play a part,
Because in light, the light goes in. And light and oxygen.
They're reading like what process CO2 synthesis.
Yeah, which uses them.
Yeah.
Water and oxygen.
CO2 and H2O only help take off.
Yeah. Water and CO2 limit the intake on the cow. Nitrogen is growth.
Okay, available CO2. Which process is that going to limit? Light reaction or dark reaction, or the Kelvin cycle?
Kelvin.
The Kelvin cycle. Okay, how about nitrogen? Any ideas there? Rubisco, yeah, the Kelvin cycle. So we'll hit that in just a second. Our next couple of slides are going to go into that a little bit more detail. How about water, light or Kelvin? Light. Any idea on pollutants? Potentially both. Maybe light. Okay, we're going to dive into that one a little bit more through our case study today. But as you guys can see, you can start thinking about where these limits are going to come in. We're going to focus on nitrogen for a minute. This should be a review for those of you who have taken Bio 113. If you haven't taken 113, it might be a review for you anyways. How do plants acquire nitrogen?
Consumption, guys. They eat it. This is a false dilemma. This is a false dilemma.
Okay, good. Option D, majority through the roots. Anyone for bonus points? Remember the process through which plants acquire nitrogen from 113?
Nitrogen fixation.
Yes, nitrogen fixation is going to be a key part of that because without it, we can't get the available nitrogen from the atmosphere into the plant roots itself. Okay, we've got our nitrogen cycle. Nitrogen fixation is a huge, huge component of it. How do plants actually get that nitrogen once it's been fixed into their roots? Absorption is going to be part of it. They're pulling it in. Bobby? It's not, well, it could be pulled up with water in transpiration. Katie?
isn't there like a hydrogen pump, or they're pumping hydrogen into the soil and then that kind of leaves the rest of the minerals to want to be soaked up into the...
Yeah, they're pumping hydrogen ions into the soil to change the gradient, and so that way these positively charged ions can come into the plant roots. Anybody remember the name for that? Starts with a C. Cation exchange. Good, okay. We aren't going to go into a lot of detail about nitrogen because that is in the domain of 113. But take a look at this model. Okay, we've spent a lot of time with carbon. Pools, fluxes. Which ones have the most overlap with the carbon cycle? The pools or the fluxes? What do you think? Pools or fluxes? Which ones seem to have more overlap? Swap foxes, what do you guys think? Pools or fluxes? Pools. Yeah, pools look like they share a lot with the carbon cycle. The fluxes look pretty different, don't they? This is where we see things like nitrification, nitrogen fixation, denitrification. So those fluxes are a lot different, but the pools where the nitrogen is moving through are pretty similar. So we know that our plants are going to acquire nitrogen from the soil pool of nitrogen that has been fixed and made available to them. They're going to acquire it through their roots through cation exchange. This is also a review question. Why is nitrogen so essential to photosynthesis? Talk about that at your tables. What's that key role?
The article said it was part of taking in Oreos.
It's the enzyme.
How it allows it to reduce like third carbon,
Yeah.
right?
It's the whole thing of biomass.
No, but it takes
Without Rubisco, we would not be able to eat.
What's everyone's favorite enzyme? Rubisco. Yes, Rubisco. Okay, we talked about Rubisco as before, saying that this enzyme is the most important because it is the one that pulls in CO2 from the atmosphere, takes it from a gaseous form, and allows it to be fixed into our molecule of sugar. And without nitrogen, we can't build Rubisco. So Rubisco is a protein or an enzyme, and it is composed heavily of nitrogen. So that is why, as we're building our warrant here, why nitrogen is so important. So without excess nitrogen in the environment, what's going to happen to the Kelvin cycle's output? Increase, decrease? What do you think? Show me with your hands. What do you think? Increase, decrease? Okay, decrease. We are going to see a decrease in the output if we do not have enough nitrogen to fuel the input to this cycle. So let's go back and revisit our graph. Let's say that in our experimental setup, we have pumped in CO2 into a field, and we've been keeping the CO2 on the field for a certain amount of time, and we've started to see a leveling off of CO2. We're going to now fertilize the environment with nitrogen. So at a time point, towards the end of our graph here, we're going to add nitrogen, and I'm going to ask your teams to make a prediction. Okay, if we add nitrogen, just a one-time fertilizer application of nitrogen, what's going to happen if we continue on in time? I'd like you to sketch this one in your notes. So add this pulse of nitrogen to the environment. You can talk with your table, but everybody should put this one in their notes.
Yeah, I'm pretty sure it's true.
What's true?
That's true.
I would be happy to help you that, Rachel. I promise.
I guess think.
Oh, productivity.
I think it's going to stay on.
Theoretically, because of their pregnancy, you could run out of actually run out of the other sources, which can cause them to go back down to where it was. Maybe not as far. We just don't know. Yeah.
What I'm saying though is that little plant taking CO2 and then CO2.
It will match it because if the plant stores excess CO2, that's going to create another pathway that's from respiration, and that's not great. It actually makes them lose weight. They'll take it up in proportions. If we don't take it up and store it unless they're bad.
I don't know. In my job,
Yes, they're ready to go. But like, for that.
Plateau with
Okay, check your drawing. May not look exactly like this, but you're seeing a pulse, an increase in that photosynthetic rate, in that NPP rate for a little while, because we've provided nitrogen. So if we provided nitrogen, how come, what's the warrant here behind why we see a spike? Which process is running at a higher rate? The Kelvin cycle, part of photosynthesis. Because we were able to take in more CO2, put it into the dark reaction or the Kelvin cycle, we can run our photosynthetic process at a slightly higher rate. So nitrogen, a fertilizer pulse, is going to pop us up for a little while, and then, again, the research gets a little fuzzy. Does it stay maintained, or do we see a crash? Part of that varies by biome. It also brings into our other limiting factors, okay? Air pollution and water availability. Most individuals right now are thinking that water availability is the biggest limit to photosynthesis. And that's because nitrogen is used pretty widely on our soils. The article talked a lot about nitrogen deposition. Did you guys see that in the probably 4th or 5th page? Talked about how much nitrogen is being used in the United States and the fact that there's actually maybe too much nitrogen that's going to be detrimental to our plants. So we're thinking water might actually be more limiting than even nitrogen in this process. Feeling okay with the impact of nitrogen on photosynthesis? Yes, no?
Yeah.
Yes. Okay. So I'm going to ask you guys to take a moment here to pause and process. Make sure you have the warrant solidified. So you've got your claim and evidence really nicely on the board, but make sure you get your warrant in your notes. What's the warrant that increasing CO2 concentrations in the atmosphere will not indefinitely increase photosynthesis? Make sure you have that one down.
What is this?
Everything is based off like the tools that are available in this area. It's like nitrogen, water, whatever. And like those tools are obviously going to be depleted more quickly. Yeah, limited more quickly. So like it's a total cycle. So like, but if you're increasing one part of the cycle, it's going to affect the entire cycle. And those are limited resources, nitrogen and hydrogen, or water. So they would deplete over time.
So, more concisely, increased CO2 levels will not decrease photosynthesis because other nutrients play a role, which are limited resources to pools.
So last class, what we did was introduce this idea of a greenhouse gas, and we talked quite a bit about CO2 as being a greenhouse gas. These are a list of some of the other greenhouse gases. All of these molecules act in the same way in the atmosphere that CO2 does. They grab onto that energy and trap it, reflect it back down to the atmosphere. So all of these function very, very similarly to the CO2 model that we worked with before. Anything surprise you on this list? Water. Yeah, water vapor is a big greenhouse gas. Why? It heats up pretty easily. What do you guys notice out here, Bradley?
It's plentiful.
It's plentiful? What did you guys notice yesterday when you walked outside? It was humid, right? Lots of water vapor in the atmosphere yesterday. Okay, that felt warmer to us, didn't it? When we go outside when it's humid, we tend to feel warmer as a result of the increased water vapor in the atmosphere, which is trapping heat around the surface of the earth. So we have carbon monoxide, main added pollutant to the environment. It's coming from what source? Burning of fossil fuels, combustion, our vehicles. Okay, nitric oxide, that's N2O. We're going to look at that one today. Where is CH4 from? Yeah, it's methane, and it's from cows. Okay, their anaerobic fermentation will produce methane. Methane is an extremely potent greenhouse gas, meaning it has a higher warming potential than our CO2 does, but we don't have it in as much abundance in the atmosphere as we do CO2. And then we have ozone. You guys probably grew up hearing about the hole in the ozone layer. Okay, ozone is protective, but too much of it can also be a contribution to this thing that we call warming as a result of our greenhouse gases trapping in the atmosphere. We are going to spend some time thinking about how all of these different greenhouse gases interact with photosynthesis, or NPP. Below on pages 318 and 319 gives a description of these gases and how they impact photosynthesis. So what I'm going to ask you guys to do, you can erase your wall space, but go ahead and create a model that shows how these greenhouse gases impact or relate to photosynthesis, or NPP. So I'll let you guys do that as a table, and then you're going to look at some data from these gases.
I know. I saw somebody yesterday. Call and lives. I saw a couple of weeks ago when I went home for this break. I was like,
It changes.
Yeah, Jenny.
Just a random question. So what are C3 and C4?
They are two different photosynthetic pathways. So C4 is a different pathway than what you guys learned about, which is C3. So you guys were doing quite a bit with the C3 pathway. C4 plants they often live in environments where there's a limiting resource in some way. Not always, but they tend to. And so they have a special mechanism for storing CO2, which prevents them from basically losing weight, which is what they would do if they run a C4. It has to do with they call it based on the amount of carbons that are formed in that first carbon compound when CO2 is fixed. So it's either a 3-carbon or a 4-carbon. Yes.
Where is that? It's probably on the bottom.
And they think that it's in the U.S. national vibration atmosphere. I was wondering what the heck that equivalent is for those two things.
So
We don't really get into it yet. Here in class chemistry is just the corroboration. It's just on corroboration of sediment.
Oh, yeah.
entirely from the environment.
So they like
They
that.
don't generate their own heat. So they
No, like the U whatever it's like. Now those ones call the U.
Scarier.
I feel like yeah, those are like faster now too. Like they know they exist, but they
This is our future. I didn't say it was called GS.
I don't know.
Or does it test to have it?
Yeah, but I wish that we would know other than it requires nitrogen. I feel like it's a lot more complex than just a nitrogen. What form of nitrogen? Oh, it can only take one form.
That's around. They said I brought it in. It's just like, oh, we gave you the play. I was like, it's for you. It's like, oh, okay. I was like, is it real? Like, yeah.
Yeah,
Like, yeah.
see, if we add more CO2, it'll take out more. I don't know if I'm right or not. There are other limiting factors. Which
So we went to Mother's Day
has a
and like gave her and I was like, look, I bought this hat for me.
Okay, let's go back together and think about your models. Lots of you created very different models. So we got a couple graphs, we got some visual, we have a box and arrow. All of these are good representations of what's going on in this scenario. So ozone is kind of a double-edged sword for us. Ozone is going to be aided, its creation is going to be aided by a number of these other greenhouse gases. So we can have kind of a multiplication effect. As we get more and more greenhouse gases in the atmosphere, we can get more and more ozone. So this model shows us that carbon monoxide can lead to the creation of ozone, as does nitric oxide, in combination with particles that we get in the atmosphere that we often call volatile compounds. These come from burning different plastics. They come from paints. If you guys have seen paint containers, if you've done any painting, they say VOC free, volatile organic compound free. They're trying to change the way that paints are created so that they're not creating as much volatile organic compounds, which are going to go in the air and react with a lot of these greenhouse gases. Water could be an increase in photosynthesis if we get enough of it, and there's nothing else limiting, so that one could actually have a positive impact, as could nitric oxide, especially if we just get the nitrogen component from that. That could yield an increase in photosynthesis as a result. But it could also feed into and develop ozone. Ozone is going to shade out our plants. It's going to prevent sunlight, those photons, from actually reaching the plants, and so we're going to see a decrease in photosynthesis in that process. So these are complex. They don't act in isolation. That's one of the big take-homes from thinking about these greenhouse gases, is they really don't act by themselves. They're interacting with one another, and their impact on plants isn't straightforward either, because it really depends on which other greenhouse gases are also present. What I have to wrap up our time today is a closer look at nitric oxide. I have a very short case study that gives you a little bit of introduction to nitric oxide. And then on the back side, there are some data that are going to ask you to make a graph and to interpret it. And I'm going to ask you to do this as an end point for today and bring it back with us on Wednesday when we will look at the data. Unless you guys move, unless it doesn't take you as long, then we'll look at it today, but I'm thinking next time. So I'll let you work on this. Partner tables, independent, your choice. guys have about 1 minute remaining before the end of class, so whatever you are not completed with at this point, you'll want to think about finishing and bringing back next time. Let's look back at our learning objectives for today. We defined CO2 fertilization and nitrogen fertilization, which is what you guys are working with right now. You evaluated the claim that increased CO2 will increase photosynthesis. You're looking at the role of nitrogen, air pollution, and CO2 on this impact of increased NPP and photosynthesis. and you're evaluating data on nitric oxide and drawing conclusions. So we will pick up with the data on Wednesday. I'll see you guys in lab. Remember to bring your posters in a digital version. I'll see you guys there. If you would erase your walls too, that'd be great. Thank you.